Today we're going to follow up talking about continuity of a function. Today we're going to focus on continuity of a function on a closed interval. Continuity of a function on an interval which actually does include the endpoints. Then we're going to introduce a theorem called the intermediate value theorem, which is the first theorem in this class which can really only be applied to functions which are continuous. This theorem is completely invalid and useless when you're working with a function that has discontinuities. So the definition of continuity on a closed interval is quite different from the definition of continuity on an open interval. Now, before I get into the differences between those definitions, I want to make sure that we're clear on what a closed interval actually is. A closed interval is an interval which includes both of its endpoints. So that's signaled by having a bracket on both the left and the right side of the interval. The brackets are the sign that both A and B are being included. In other words, that A less than or equal to X less than or equal to B. Now when someone says that a function f of x is continuous on a closed interval AB, when they say something like that, that statement carries a lot of information about what the function f of x is doing. It's giving you three different pieces of information in this one statement. The first thing that this statement tells you about f of x is that f of x is continuous on the open interval from A to B. So what this means is that if you take any x value strictly in between A and B, if C satisfies being strictly between A and B, then the value of the function at C is an exact match for the two-sided limit at C. The second thing that this implies is information about what's happening at A itself. The second piece of information that we have is that the value of the function at A is equal to the one-sided limit, what you get when you approach A from the right side. Notice that the only thing that has to be true is that the function's value has to match the right-sided limit. Based on the data in this bullet point, who cares what the limit as x approaches A from the left side is doing? Correspondingly, when someone says that f of x is continuous on the closed interval from A to B, they're saying that at the opposite endpoint, when x is equal to b itself, the function's value is a match to the limit as x approaches b from the left side. So basically, in this definition, who cares what is happening to the right of B? The right-sided limit at B does not matter at all for this definition. Now, this might seem really strange. The definition for continuity on an open interval was just that the function had to be continuous at every x inside that interval. But for some reason, when we are including the endpoints, when we look at the closed interval for A to B, the definition gets way more complicated. At the endpoints, we are only considering one-sided limits instead of two-sided limits. So what's the reason for this discrepancy? And the reason is going to be a little cheap, I think. My explanation will be a little bit cheap, but I do think it's the truth. When we define something, we define it just for our convenience. When we create a new mathematical term, It's just for us to quickly and efficiently describe a certain situation to someone else. So when we create a word, it's because that situation arises a lot, and we need to talk to other people about that situation quickly and efficiently. This definition was created this way so that we could do things like state theorems using a minimum of words. It's just like any other jargon or slang, right? When you're online, you see all these acronyms floating around. It's just because those phrases came up so often that it became cumbersome to keep saying the entire phrase in full over and over and over again. So those phrases were shortened, and that's what's happening here. This huge triple bullet point is basically just a long phrase that comes up often. And so all that we have done is taken this gigantic phrase and shortened it into basically a mathematical acronym. Instead of writing all of this stuff, then all we have to say is f of x is continuous on the closed interval ab. Way more effective. So let's return to our old friend, our very familiar graph, and let's ask ourselves the question, at which of the following closed intervals is the following function continuous? The first interval that we're looking at is the interval from 3 to 5. And I'm going to indicate it with a bracket to remind myself that I am looking at the closed interval from 3 to 5. Now let's consider the definition of a closed interval. One of the requirements was that the function had to be continuous at every point strictly between the two endpoints. But the problem is that directly in between 3 and 5, we have this discontinuity at 4. So our function is not continuous on the closed interval from 3 to 5 because there is a discontinuity directly in between our endpoints. Let's check out the interval from -4 to 2. The interval from -4 to 2 is in pink brackets on the left-hand side. And this is where the discussion starts to get a little bit more interesting. Now, if I look strictly between -4 and -2, if I forget about the endpoints for just a second, there are no discontinuities strictly between -4 and -2. So far so good. So far, the function is continuous at every point strictly between -4 and -2. Now let's check out what's happening with this function at the left endpoint. What's happening with this function at -4? The requirement at the left endpoint was that if we snuck up on the left endpoint from inside the interval, that sided limit had to match the function's actual output. But notice that if we approach -4 from within the interval, if we approach -4 from the right side, then that limit is equal to, looks like 3, and the function's value is also equal to 3, because there is no hole in the graph here at -4 that might cause any problems. However, if I consider the right endpoint of this interval, in this case, if I approach the right endpoint from inside the interval, then those orange arrows are pointing to a location where the y value is equal to 1. So the limit as x approaches -2 from the inside of the interval, from the left side, is equal to +1. However, there is a hole in the graph right here at -2, and the actual filled dot, the value of the actual function, is down here somewhere -1/4 or something like that. So there is a discrepancy between the value of the function at the right endpoint and the limit of the function as we approach that endpoint from the inside of the interval. As a result, the function is not continuous on the closed interval from -4 to -2. Let's test it on the closed interval from -2 to 0. It goes from right here to right here. So the first thing that I'm going to check is, okay, are there any discontinuities in this function strictly between the left endpoint and the right endpoint? I'm not seeing any discontinuities strictly between -2 and 0. So the next thing that I'm going to check out is what's happening at the endpoints. For example, I might focus my attention at what's happening at the right endpoint. So I'm going to approach the right endpoint, and I'm going to approach it starting from inside the closed interval. And those green chevrons are pointing to a location on the graph where there are no holes. So the limit as I approach that location from inside the interval is a match to the function's actual value at that endpoint. So far, so good. Now if I try it for the left endpoint, I'm now going to approach -2 from inside the interval. This time, the pink chevrons are pointing to a location on the graph where we have a filled dot. And that filled dot is a sign that the limit and the function's value actually agree here. So in this interval, -2 to 0, all three of the continuity requirements are satisfied. So the function yes is actually continuous on this interval. And let's check out from -6 to -4. -6 to -4 lives right here. Now if I look strictly in between -6 and -4, once again there are no discontinuities strictly between those two endpoints. If I creep up on the right endpoint at -4, if I approach that location from the inside of the interval, then those chevrons are not pointing to a hole, they're pointing to a valid location on the graph, so limit and value match. And if I approach the left endpoint from inside the interval, then those values also match. So this function is continuous on the closed interval -6 to -4 as well. Now, if you have a function which is continuous on a closed interval, you unlock the ability to use a very special theorem called the intermediate value theorem. And to set the stage and explain why this theorem might be useful, I want to go back and remind us that, we've spent a lot of time in mathematics solving equations. But we've encountered plenty of equations where you try and solve them, but it turns out that they don't have any solutions at all. A simple example of an equation with no solutions would be something like x squared plus 1 equals 0. This equation has no solutions because it's not possible to square a real number and get a negative result. Now that was, relatively speaking, obvious. Where it gets a lot more complicated is in an equation like the one below. Does this horrific equation have a solution? If somebody asked you to try and solve this equation, would it even make sense to devote time, to devote effort, or to devote computer resources to trying to find a solution to an equation like this one? When compared to the kinds of equations that you would get in a real-life application, even this equation in the second example is really simple. Real-life equations are more likely to be sufficiently complicated that even if you solve them via computer, the amount of time that the computer would need to solve the equation is non-negligible. So the question is, are there any computationally efficient ways to tell in advance whether or not an equation has a solution? If you try and solve this equation, is there any hope of actually finding a solution, or are you on a doomed mission? And that's what the intermediate value theorem is designed to provide. It's designed to provide you a quick, computationally efficient way to determine in advance whether a complicated equation has a solution or not. The requirement to use this theorem is that you're working with a function which is continuous on a closed interval from a to b. If you are in those circumstances, the first thing that you want to do is you want to check out the y values at the endpoints, f of a and f of b. If you have a third value, let's just call it d. If you have a third y value, which lies somewhere between the y value at the left endpoint and the y value at the right endpoint, then the equation right here, f of x equals d, definitely has at least one solution. Now, just a quick comment about sort of what intermediate value theorem is doing and why it works. So you have a function which is being considered between two x values, a and b. Now, the function is assumed to be continuous. And what that means in practice is that you can connect the dots from a to b. Without lifting your pen, you can draw the graph of f of x from a to b without lifting your pen. If the function were not assumed to be continuous, then there's a possibility that your function might have a break or a gap in there somewhere that would cause you to lift your pen as you moved from a to b. If your function is continuous, and you're trying to figure out if the function ever reaches a height of y equals d, if that d value is between the outputs at the left endpoint and at the right endpoint, because the graph is continuous, it cannot jump over the level y equals d. It has to pass through the level y equals d. And where the level y equals d meets the graph, this is where the solution lives. This isn't guaranteed to happen if the function is discontinuous. If the function is discontinuous, then y equals d might correspond to a level where the function has a break. The function doesn't actually have a solution because the graph doesn't ever cross this height at y equals d. Let's apply that reasoning to answer the following questions. So suppose we have a function f of x which is continuous everywhere. We don't have to worry about any discontinuities or breaks or gaps at all. Someone says, based on the data in this table, how many solutions must there be at a minimum? How many solutions must f of x equals 0 have? So I'm going to draw a little sketch of this situation. Now I have drawn these data points from the table, but the function in this problem is continuous. which means that the graph of the function can't have any breaks or gaps or holes. The actual graph of f of x would have to connect the dots smoothly without ever lifting the pen. So here is an example of one possible continuous f of x. A continuous function would have to connect the dots without the pen ever being lifted off of, in my case, the tablet. So now let's check. If I connect the dots without lifting the pen, because f of x is continuous, how many points does the height of the function equal 0? Well, I can detect one such point where the function's value changed from positive 110 to negative 120. The value y equals 0 is between the y value at this red point and the y value at this other red point. So because y equals 0 was between these two y values, one solution is guaranteed to be achieved at that location. Moving through the graph, I see right here where the data in the table transitions from a negative y value to a positive y value. Y equals 0 is between the output at this red dot and the output at this red dot, so that y value must correspond to a solution. Once again, over here, the graph transitions from positive to negative, so it must cross 0 along the way. And I see another instance of this here, where now the graph changes from negative to positive, which means that there are at least 4 solutions to this equation. Now for our final few applications of the intermediate value theorem, let's consider the following two thought exercises. So suppose a car is driving and we have two pieces of data about the car. At 1 p.m. we know that the car was driving 40 miles per hour. And then an hour later at 2 p.m. we find that the car was driving 60 miles per hour. So is the following statement about the car guaranteed to be true? Or potentially could it be false? Must it be true that the car was driving 50 miles per hour at some time between 1 and 2 p.m.? I'm going to say the answer to this question is yes. We could represent the car's speed by a continuous function of x. Why would speed be continuous? Because a car's speed cannot suddenly change from 20 miles per hour to 70 miles per hour. A physical car, has to smoothly accelerate from one speed to another. What we found is that the speed at 1 p.m. was equal to 40 miles per hour, and the speed at 2 p.m. was 60 miles per hour. And the speed that they're interested in, 50, is between 40 and 60. So that speed of 50 miles per hour was achieved at some time between 1 p.m. and 2 p.m. This is a result of the intermediate value theorem. At time 1 p.m., the car was going 40 miles per hour. At time 2 p.m., the car was going 60 miles per hour. Who knows exactly what it was doing, but at some point, in order to get from 40 to 60, it had to accelerate through 50 miles per hour. To show an intermediate value theorem cannot be used, and why continuity is important, let's consider the following situation. In this case, we've got a bank account, and on the 12th of September it contains $1,200. Then at a slightly later time, the 13th of September, the account contains $1,500. So must the account have contained $1,400 at some point between the 12th and the 13th? I think that no. The bank account was not guaranteed to have contained exactly $1,400 at some point between these 2 days. The issue in this case is that the amount in the bank account is not a quantity that changes continuously over time. The amount in a bank account can totally jump up or down by large amounts. So it's completely feasible that on the 12th of September, the value in this bank account was $1,200, and then someone made a sudden deposit, and the value in the bank account jumped to $1,500. Without ever having to achieve this intermediate value, this middle value of $1,400 along the way. So I want to show you an example of intermediate value theorem in practice. This example might seem a little bit chaotic, but unfortunately, as we get into more and more realistic applications of mathematics, the larger the amount of chaos will become. So a typical situation is this. We've got this ever so slightly ugly equation where we have x minus 1 to the third power plus x plus 3 to the second power equals 5. And we want to know if this has a solution. Now, for us humans, already this equation would be a huge pain to actually solve. But this equation honestly is pretty simple for a computer to solve directly. So I'm going to stand back and acknowledge the fact that the equation in this problem is significantly simpler than any kind of real-world equation that we might want to apply this theorem to. And I'm just going to use this equation to demonstrate the overall technique. Now, the thing that I'm going to try and set up is this condition in the intermediate value theorem. I want to set up something that looks kind of like this because I have a statement in intermediate value theorem which says, hey, under these conditions, here's an equation and you're guaranteed to have at least one solution. So I'm going to try and express this problem using some of the language and some of the notation of intermediate value theorem so that hopefully I can use this theorem to answer this question. So the intermediate value theorem is being expressed in terms of a function of x equaling a constant. Currently, my equation doesn't have a function in it, but what I'm going to do is I'm just going to use function notation in this problem. I'm going to let f of x be a stand-in for this big mess containing the x's on the left side. Because of that, our equation becomes f of x equals 5. So I'm trying to determine if this equation, f of x equals 5, has a solution. So, still inspired by intermediate value theorem, I'm going to try and trigger some of the conditions that would allow this theorem to be used. And there are really two conditions here that need to be satisfied in order for the conclusion of the theorem to kick in. The first thing that needs to be true is that I need to make sure that the function called f of x is continuous. So let's check that out. Now the function f of x in this problem is a polynomial. And polynomials are basically as good as it gets when it comes to continuity. Polynomials are completely smooth and they don't have any holes or breaks or asymptotes of any kind, So these polynomials are continuous everywhere. So no matter what interval a, b I consider, polynomials are so well behaved that a polynomial would be continuous on any interval, no matter what. So that's the first sort of condition that needs to be true. And now I need to work on the second condition in this theorem. If I can get this second condition to be true, then both of these requirements are satisfied, and I can actually conclude that the equation in my problem does have a solution. So now, really what I need to do is I need to try and trap this constant 5 between two function outputs. Or in other words, I need to find two outputs for this function, one of which is larger than 5 and one of which is smaller than 5. So really what I'm going to do is I'm just going to take f of x and I'm just going to start throwing x's into it. I'm going to plug x's into this function more or less at random to see if I can eventually come up with an output which is smaller than 5 and an output which is larger than 5, so that my 5, my constant value, is between those two outputs. So at random, let's just start plugging stuff in. For example, I might start with f of 0. 0 is a great number to start with, generally speaking. If I plug 0 into this function, then I get negative 1 cubed plus 3 squared, and the result of that is 8. Okay, so I have achieved one output which is larger than 5. So now my goal is to get an output which is underneath 5, which is smaller than 5. So let me plug in the next easiest value. Maybe I'll plug in 1. But it looks like if I plug in 1 to this function, the result of that is going to be 100. So that's not going to work. I'm still looking for a value which is smaller than 5. I already have my y value which is larger than 5. So maybe I'll try a negative x value, something like minus 1. And if I plug in minus 1 to this function, it looks like I get negative 2 cubed plus 2 squared. So I think that's minus 4. I have my value 5, which I'm trying to find, and I've managed to squeeze 5 between two function outputs. I've managed to squeeze 5 between f of 0 and f of minus 1. As a result of that, because I had a continuous function and I squeezed 5 between these two outputs, I can be guaranteed that yes, my equation actually has a solution. And actually the conclusion is even slightly better than that. Because I specifically managed to trap 5 between f of 0 and f of minus 1, I can actually also conclude that the solution's location is going to be somewhere between minus 1 and 0. We didn't state that in the theorem, that's just an additional bonus fact. So not only is there a solution, but now you have a pretty good idea of where to find the solution. The solution can be found somewhere between x equals 1 and x equals 0. Now this might seem like an awfully strange way to determine whether or not an equation has a solution. And it might seem like a fairly inefficient way to answer a question like this. And that's true. This is an inefficient way to answer a question for an equation that is this simple. For equations that are more reflective of the kind of thing that you might get in real life, this process actually does occasionally save time. When it comes to how computers solve equations, the time that it takes a computer to solve a complicated equation can actually be pretty large. Compared to that, the time that it takes a computer to plug a number into an equation is super short. The time that it takes to plug a number into an equation is so short by comparison that sometimes it's worth it to even plug in hundreds or thousands or hundreds of thousands of x values into the equation until you get an output which is larger than the d value and another output which is smaller than the d value. That concludes today's material. We discussed the definition of continuity on a closed interval from A to B. Then we began to look at the intermediate value theorem, which is a theorem for continuous functions. We took a look at a mathematical application of intermediate value theorem to determine the minimum number of solutions to an equation. We looked at some real-world scenarios where intermediate value theorem could or could not be applied. And then we took a brief look at a more authentic use of intermediate value theorem when it comes to determining whether a complicated equation has a solution.